Welcome back. We are now wrapping up our discussion of programming SDNs with a lesson on event-driven software-defined networking. The idea behind event-driven SDN is that network configuration often must respond to changing network conditions, such as peak and off-peak times, shifts in traffic load, security events, and so forth. In fact, much of network configuration is really just about event processing. For example, consider the following example policies. The first says rate limit all bit traffic between the hours of 9 and 5. Another example might be to say, don't use more than 100 gigabytes of my monthly data quota for Netflix traffic. Another policy might say, if a host becomes infected, redirect its traffic to a captive portal where it can download software to patch the vulnerability. Based on the observation that much of network configuration involves responding to events involving users, time, and history, we've designed an event-based SDN controller that responds to dynamic events in the network and pushes flow table entries to switches based on both the policy that the operator specifies and the state of the network at any given time. In addition to matching on flow table entries, event-driven control domains allow flow table entries to be changed based on time, history, or user. For example, flow table entries might be updated depending on whether the time of day was peak or off-peak, or whether the time of the year was during a peak time or a holiday. History might involve keeping track of the amount of data that a user uses, or how much traffic they've been sending over a particular time interval, and adjusting flow table entries based on that historical information. The appropriate flow table entries that should be installed in response to these events also might depend on the user of the device experiencing those events. For example, if an infection is detected, the network operator might want to take different action depending on whether that device belonged to a top-level executive or a guest on the network. Resonance is an event-based SDN controller that uses a set of finite state machines to keep track of various network states. A state is a set of domain values, and various events trigger changes in these domain values or state transitions in the controller's finite state machine. When the controller experiences a state change, for example, as a result of intrusions, fluctuations, the arrival and departure of hosts, and so forth, the controller might install a different set of flow table entries. To keep track of state changes, Resonance has a dynamic event handler that listens for external events and adjusts states in response to those events. Based on the state that the network is in at any given time, the controller then decides to update its set of actions, or in other words, the flow table entries that reside on the switches. To consider the utility of Resonance, let's take a real-world example from a campus network involving access control. Without SDN, the sequence for authentication might go something like this. A new host arrives, and the switch sees a new MAC address, at which point it uses a VLAN query protocol to ask the VMPS server to map the MAC address to the appropriate virtual LAN. Because the VMPS hasn't seen this MAC address before, it assigns the host to a virtual LAN with a private IP address. On that virtual LAN, the host can't get anywhere except to a web authentication portal. If the host successfully authenticates, the VMPS can then remap that client to a public virtual LAN with a public IP address. At this point, the host needs to get a new IP address. If it's using DHCP, or the Dynamic Host Configuration Protocol, which most devices in this environment use to get an IP address, the only way to guarantee that it can get a new IP address is to reboot the machine, or ask the user to reboot the machine. At this point, a vulnerability scanner may periodically scan the host, and if an infection or vulnerability is detected, the network administrators would like to move that host back to a private VLAN. Of course, the problem is there's no good way to do that without renumbering the host, something that's very hard to do remotely on campus networks today. So this current approach is too coarse-grained, it's static, inflexible, and prone to misconfigurations. Operators need to rely on VLANs to isolate infected machines, and they can't dynamically remap hosts to different portions of the network. For example, remapping a host in this situation requires the device to issue a DHCP request, which in many cases might mean a reboot. Monitoring is typically not continuous, and even if it is, there is no good way to automatically respond to monitoring such as a vulnerability scanner. We'd like to provide the operator a way to express policies that incorporate the notion that the state of the network may continue to change over time, and actions that the operator wants the switches to take may differ depending on the state of the network at any given time. The solution to this problem, as we mentioned, is to encode a state machine at an SDN controller. As a first cut, the state machine might look something like this. So a host starts out in an unauthenticated state, and if the authentication at the web portal succeeds, the host transitions to an authenticated state, at which point the SDN controller might update flow table entries in switches to allow traffic through to a web portal, but nowhere else. If the authentication fails, the SDN controller might quarantine the host. An authenticated host that's clean after a vulnerability scan might be moved to a clean state. If a vulnerability is later detected, we might move it back to the authenticated state, where the OpenFlow rules would limit the destinations or endpoints that the host could communicate with and the types of traffic it could send. If the host continues to be infected, we might ultimately move it into a quarantine state. Once the user removes the infection or otherwise patches his or her machine, we might move it back to the start state. So this is one example of how to encode policies into a finite state machine, but something about this encoding leaves a little bit to be desired. You can see that there are already two different things going on. There is the notion of whether the host is authenticated or not, and there's the notion of whether or not the host is infected. It would be nice to encode separate state machines for each of those modules, and then compose those state machines to produce a single policy based on a set of states. Fortunately, we have a mechanism for doing that we learned in the last lesson. Sequential composition allows the operator to encode multiple state machines at the controller, one for authentication and one for the intrusion detection system, or the scanner. Given the states of each of these individual finite state machines and the policies associated with each of these states, the programmer can then sequentially compose the policies associated with the states of each of these finite state machines to produce a single policy that can be installed in the switches. Let's take a look at resonance with sequential composition in action. We will again use our 3-node topology with a single switch, and we will attach a pyretic controller that this time is running resonance. We will also simulate the presence of an authentication module or an intrusion detection module, each of which might send JSON events to the controller to indicate that a particular host has been authenticated or that it has been determined to be clean or vulnerable. Here's the code that implements the auth state machine and the associated policies. You can see that we compose a dynamic resonance policy with the dynamic learning switch policy, and that the policy associated with the dynamic resonance policy is to perform a parallel composition of the packets query and the default auth policy. We initiate the auth policy with a finite state machine, auth FSM, and we start an event listener to listen for JSON events that indicate changes in the state to the auth FSM. The default policy for auth policy in the resonance policy.py file looks very similar to our firewall policy from the last lesson, except now we are performing a parallel composition to return packets from any host whose source IP address is in the auth hosts list. Let's have a quick look at resonance in action. First, we will start our 3-node mininet topology, and we will start the resonance controller. You can see that an OpenFlow switch is connected and that we currently have no authenticated hosts, so that when H1 tries to ping, no packets get through. We can send JSON messages to indicate that host 1 and host 2 are authenticated. So you can see that the event listener has now seen that host 1 is authenticated, and packets from host 1 are being forwarded to host 2, but not in the reverse direction. Now if we authenticate host 2, we see that packets are now flowing between host 1 and host 2. As mentioned, we can expand the resonance control policy to include the sequential composition of policies that result from the output of multiple finite state machines, as highlighted here in the resonance main file. In this case, we can start the resonance controller as before, and now we are keeping track of which hosts are authenticated and which hosts the IDS scanner determines to be clean. Packets will only be allowed from hosts that are both authenticated and clean. Let's start by pinging H2 from H1. We can see that no packets will be allowed through until we both authenticate both host 1 and host 2, and the IDS scanner determines that both hosts are clean. Once both hosts are determined to be both authenticated and clean, packets begin flowing between that pair of hosts. In summary, network configuration and policies must often express what should happen in response to events at different times of day and for different groups of users. In short, network policies are dynamic, and the controller should maintain a state machine that maps to different sets of policies depending on the state of the network at any time. These state machines can help determine what rules are appropriate to install, and composition can help keep these finite state machines simple.